Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 16 of Algebraic Topology. As you know that we are reviewing some machinery from homological algebra, and today's our third in the series of those lectures. In today's lecture we will review what are chain complexes and how we use them to calculate the homology. So what is a chain complex? Starting from the definition of the chain complex, so we usually denote a chain complex with C, this subscript star, or C star with this partial sign. This partial sign is indicating the kind of mappings between the different objects of this C star. Okay, so what is this chain complex? It's basically something like this, okay, and it's doubly infinite sequence of modules. So it goes on these two sides, and so it is doubly infinite, and it's a sequence of modules, and so each element CQ plus 1, CQ minus 1, up to so on, each and every element in this doubly infinite sequence is a module over some unital ring together with these homomorphisms. Okay, so we have homomorphisms partial I from Ci to Ci minus 1. Of course, we have partial Q minus 1 from CQi minus 1 to CQi minus 2, up to so on, and we collectively denote these partial i's with this partial, and that's why we write, sometimes we write this partial sign over here just to say, just to name the homomorphisms between two objects of this chain complex. And the important property that they should satisfy is that partial I composition partial I plus 1 is equal to 0. Okay, so what does this condition imply? Okay, so basically we are saying that if I take composition of any two composite maps, then it is 0. In other words, if I take an element of CQ plus 1, so CQ plus 1, let's take an element, let's call it C, and when I apply partial Q plus 1 on it, and I'll get an element of CQ. So basically there is an element partial Q plus 1 of C in here, but when I apply partial Q again on partial Q plus 1 C, then of course I get an element of CQ minus 1, but it is 0. So partial Q plus 1 of C is 0. So in other words, this element partial Q plus 1 C belongs to the kernel of this partial Q. Okay, because so what is kernel? So kernel of partial Q is set of all elements of CQ such that partial Q of X is 0. So set of all elements of CQ taking such that partial Q takes those elements to 0. And in this case partial Q is taking partial Q plus 1 C to 0, so that's why this element partial Q plus 1 of C belongs to kernel of partial Q. So in other words, whenever I take elements of CQ plus 1 and find their images in CQ, then those elements belongs to the kernel of partial Q. Okay, because I didn't impose any condition on C, so C is any element of CQ plus 1. So take any element of CQ plus 1, apply partial Q plus 1 on it, and gets an element of CQ, but we call it image of partial Q plus 1. So what is image of partial Q plus 1? So set of all elements Y belongs to CQ such that there exists X belongs to CQ plus 1 and partial Q plus 1 of X is equal to Y. So in other words, let's say this is CQ, then some elements of CQ are images of elements of CQ plus 1. So let's call them image partial Q plus 1. So these are all elements of CQ such that which are images of elements of CQ plus 1, and these elements when we apply partial Q again will go to 0. So in other words, every element of this set image q partial q plus 1 belongs to kernel partial q. In other words, we can say that image of partial I plus 1 is contained in image of kernel of partial I. So where I is any integer. So in general this this holds for each and every integer, and or we can say that this holds for each and every node, because in this case we are considering the node I, and in this case we are considering the node CQ. Okay, so this holds for each and every node. So that's how we define a chain complex, a collection of modules and collection of homomorphism satisfying this important property that partial I composition partial I plus 1 equal to 0. In other words, composition of any two consecutive homomorphisms is 0. We have already dealt with an example of chain complex, and well, when we were calculating the simplicial homology. So what was this chain complex? So you can see that there is a 0 over here, and we defined our chain complex that they are doubly infinite. So I can take the rest of the things to be 0, 0 and 0 on both sides. Okay, so whenever there is there'll be for example, if the simplicial complex has dimension n, then all the higher dimensional free abelian groups, for example, if it is n dimensional, then Cn plus 1 of k will be 0. So I can just take zeros on the other side. So it is doubly infinite. And we also proved that for this complex we have, okay, so partial q minus 1 equal to 0. So we proved this result. Okay, so the objects are free abelian groups, and we also know that every free abelian group is a Z module. So basically it is a sequence where the objects are modules, and unital over the unital ring, because Z is a unital ring, it contains multiplicative identity. So the objects are modules over some unital ring. Okay, so what about the maps? The maps are homomorphisms. We have already dealt with these boundary maps, and we have already proved that these boundary maps are homomorphisms. Okay, so the second condition is also satisfied, and third condition we have already proved this condition, and there is a proof when we were discussing these sequences. And so this is an example of a chain complex. Okay, so how to calculate homology of a complex? So remember, when we consider this chain complex, then we defined homology of this complex. So for example, H1 was defined as, so H1 of k is equal to, so it is basically kernel. Okay, so basically Z1 of k quotient with B1 of k, and Z1 of k is kernel of this partial 1, and B1 of k is image of this partial 2. So we defined this, and we did this for each and every node of this complex. Okay, so the only condition we used here was the fact that image of partial 2 is contained in the partial 1. Okay, so as we can see in this picture, that the image of for example this partial 2 is this B1. Okay, so this is the image of partial 2, and this Z1 is the kernel of partial 1, and B1 is contained in Z1. So I should be able to take quotient, because Z1 is an abelian group and B1 is an abelian group, so I can easily take the quotient of these two free abelian groups. So this quotient is basically H1 of k. So basically when we defined the homology or simplicial homology, so we considered this chain complex with these homomorphisms, and we used this condition, and in other words we can say that these are the only three ingredients needed to define the homology or simplicial homology, and these are exactly the conditions that we imposed on the chain complex. So in other words, we should be able to define homology for any chain complex, and that's what we are going to do. So consider a chain complex, and in this chain complex, kernel of partial n is called the group of n cycles. Okay, so n is denoted by Zn C star partial, Okay, so why it is called n cycles? Unfortunately we don't have time in this lecture to define this thing, but the references of the lecture notes will give you clear resources for reading these things. Okay, so image of partial n plus 1 is called the group of n boundaries and is denoted by bn c star partial. Okay, the nth homology of this complex is this. So as you can see that we haven't done anything different here. So just take these cycles, take quotient with these boundaries, and we are denoting, so we are writing this extra partial here just to say that what kind of homomorphisms we are taking in this chain complex. Okay, so as long as these homomorphisms satisfy this condition, so we are fine with it, and that's why we write partial over here. Okay, so so basically we can replace this partial with some other homomorphism satisfying these conditions, of course. Okay, so if the modules in the chain complex C star are R modules, then the homology groups are also R modules. Okay, so we have already done this in quotient modules. Okay, so when we were discussing the first lecture, okay, so during the first lecture of our series of homological algebra, we discussed that when we have two modules, then their quotient is also a module. Okay, so these Zn and Bn are, if they are R modules, then their quotient is also an R module. So the homology groups Hn C star partial are classes of the form this. So basically we are taking quotient, and once again when we were discussing the quotient modules, so we saw that what are the elements of this Hn C star. So these are the elements of the form x plus Bn C star partial. Okay, so where x are the elements of Zn C star partial. So these are the elements of this C star partial. Okay, so it is basically a quotient module, and its equivalence classes are of this form. Okay, for fixed Zn, if I take any fixed element of the Zn, the class Zn plus Bn C star partial is called the homology class of Zn and is denoted by Zn. Okay, so in other words, if I have this x plus Bn star, so I can denote it as square bracket x. So whenever I write down an element, let's say x belongs to Hn of C star and with partial, so this means that it is an element of the form x plus Bn C star partial. Okay, so I can also say that when x is 0, so when I say that I have an element x which is 0, it means that this x belongs to Bn C star partial. Okay, so as a matter of fact, I'm not saying something which we haven't discussed. Okay, so we are basically dealing with the R modules and their quotients, so I'm just recalling them in this structure. A chain complex is exact sequence if and only if these homology groups are 0. So it's a very simple result, but it has very important consequences. So there is if and only if. So let's start with the fact that a chain complex is exact. Okay, so let this chain complex is exact. So what's the difference between the condition of the chain complex and the condition of exactness? Okay, so in the condition of chain complex, we saw that so the image of partial q plus 1 is contained in the kernel of partial q, so this is the condition of chain complex. Okay, so this is coming from chain complex condition. but now we have imposed that this is exact. So exactness says that, so this implies, so now the image of partial q plus 1 is equal to the kernel of partial q. Okay, so now they are equal. Instead of this image is contained in the kernel, now they are equal. Now how to define homology, for example, at this node h c q? So h q c star partial, so this is equal to z q c star partial quotient with b q c star partial. So what is zq? So zq c star partial, so basically this is the kernel of this partial q. And what is bq? So these are the boundaries, and basically this is equal to the image of this partial q plus 1. Okay, so now we have imposed that the image of partial q plus 1 is equal to kernel of partial q. So in other words, they are equal. Okay, so by assumption, of exactness, of course, so by assumption of exactness, we can say that this zq of c star partial is equal to bq c star partial, and which of course implies that hq of c star partial is equal to 0. Okay, so this is the one side of the result. Now conversely, assume that these homology groups are 0. So if these homology groups are 0, then of course by definition these HQs are ZQ C star partial quotient with this BQs. Okay, so if this is a 0 module, so in other words we can say that ZQ is equal to BQ. Okay, because we are saying that this quotient module is 0. So in other words, this BQ must be equal to ZQ, and this thing implies directly that the image of partial q plus 1 is equal to the kernel of partial q. Okay, so we chose this node arbitrarily. So in other words, this q varies over the set of integers, and the above results hold for each and every integer. So in other words, we can say that a chain complex is an exact sequence if and only if the homology is 0. So we can say that the homology group measures the deviation of a complex from being an exact sequence, because when the chain complex is exact, then the homology groups are 0. But in general, the homology groups for any chain complex are not 0. So basically it measures the amount of this chain complex, how different it is to be an exact. Okay, so let's see how to define maps between two different chain complexes. Okay, so these are called chain maps. So given a chain complex C star with these partials, so these partials are, so basically we are naming the homomorphisms between objects of this C star, and similarly consider another chain complex C star prime partial prime. So a chain map between these two chain complexes is a sequence of homomorphism. So basically this chain complex consists of objects and homomorphisms satisfying certain property. So when we are defining a homomorphism or a map between two chain complexes, then I need to define the maps between the corresponding objects. So basically Cn prime to Cn. So that's how it maps elements Cn prime to Cn such that the following diagram commutes. Okay, so as you can see that the first row is basically C star prime. Okay, so that's our first chain complex, and the second row is basically C star. Okay, and you can see that we are denoting the homomorphism with, in this case, in the C star prime case, with the partial primes, and in the C star case with partials. Okay, so now basically we have elements, we have objects, and from Cn plus 1 prime to Cn plus 1 we have these maps Fn plus 1, and similarly for each n we have these maps, and we have the condition, we have the extra condition that we are imposing for this map to be a chain map, is that this diagram should commute. In other words, if I take an element x from Cn plus 1 prime and I apply a partial n plus 1 prime on x, and then I apply Fn on it, then I can take another route from Cn plus 1 prime to Cn, and that route is first applying Fn plus 1 on x and then applying a partial n plus 1, and this condition that the diagram commutes is basically the condition that by taking any route from Cn plus 1 prime to Cn, my answer should be the same. Okay, so similarly there are many other routes. So once again, let's take y from here, follow this route or follow this route, you should reach at the same image. Okay, so that's how we define chain maps between two different chain complexes. So we know that given a chain complex, we can define homology groups. Our next aim is to understand the answer of the following question. So given two chain complexes and a chain map between them, then what is the relationship between the homology groups defined by these two chain complexes? Okay, so that's our next topic of discussion. So given a chain map between two chain complexes, then what's the relation between the homology groups of these two chain complexes? Now let's see how to answer this question. So given two chain complexes and a chain map between them, so in other words we have a sequence of homomorphisms Fn plus 1, which is a homomorphism between Cn plus 1 prime and Cn plus 1, and Fn, which is a homomorphism from Cn prime to Cn up to so on, and this diagram commutes. Okay, now let's see how to define the relation between the homology group of this chain complex and the homology group of this chain complex. Now observe that, so if I have Zn C star prime, so basically this lives inside, okay, so Zn C star prime lives inside Cn prime, and basically it is equal to the kernel of partial n prime. Okay, now when I apply Fn on this, then it is contained in Zn C star. So similarly, what is Zn C star? So Zn C star is basically so it lives inside Cn, and it is equal to the kernel of partial n. Now I want to show that the kernel so which lives inside this is basically, when I apply Fn on this, then it lives inside Zn of C star. Okay, so let's see how to show this result. So let's take x belongs to Cn prime such that it belongs to the kernel. Okay, so let's use this space to show this result. So x belongs to Cn prime such that partial n prime of x is equal to 0. Now we can also see that this Fn plus 1 is basically a homomorphism, so it must take 0 of Cn minus 1 prime to the 0 of Cn minus 1. So basically this implies that when I apply Fn minus 1 on partial n prime of x, then it must be 0. So in other words, we follow this route, first applying partial n minus 1 and then applying fn minus 1, and we get 0 here. Similarly, since this diagram is commutative, so if I apply fn on x first and then I apply partial n on it, then it should also give me 0. So in other words, this implies that this element fn of x belongs to the kernel of partial n. Okay, so in other words, when I take any x which belongs to z and c star prime, in other words, x belongs to the kernel of partial n prime, then fn of x belongs to the kernel of partial n. So every element x of Cn prime, for every element x of Cn prime, fn of x belongs to the kernel of this partial n. So we can say that fn of zn c star prime is contained in the kernel of partial n, which is zn c star. Okay, so that's first observation. Now let's see, if I take any element of the boundary of c star. Okay, so basically if x is an element and this is image of partial n plus 1 prime. Okay, so in other words, there exists y belongs to Cn plus 1 prime such that partial n plus 1 prime of y is equal to x, because we assume that x belongs to the boundary. So in other words, there must exist an element of Cn plus 1 prime such that when we apply partial n plus 1 prime on that, then we get x. Okay, so now let's consider this expression. So first apply partial n plus 1 prime on y and then apply fn on this. Okay, I should get the same answer due to the commutativity. So the first expression is this root and the second expression is this root. So second expression is this. So first apply fn plus 1. So first apply fn plus 1 on y and then apply partial n plus 1. So in both cases I should get the same answer because the diagram is commutative. So what does this imply? So partial n plus 1 prime of y is equal to x. So just write fn of x here. And this is equal to, so there is no change on this side. So fn of x is basically image of some element of Cn plus 1. Okay, so because fn of x is equal to partial n plus 1 applied on fn plus 1 of y. So basically y belongs to Cn plus 1 prime and f of y, fn plus 1 of y belongs to Cn plus 1, and so when we apply partial n plus 1 on this element, then I will get bn of this c star. Okay, so in other words, I get boundaries of this chain complex inside Cn. In other words, fn of x belongs to bn of c star. So take an element of the boundary of c star prime and it belongs to the boundary of c star. So okay, so we have proved that if I have cycles in Cn prime, then fn of those cycles are contained in the cycles of Cn. Similarly, if I have boundaries of Cn prime, then when I apply fn on them, then the boundary is contained inside the boundary of Cn. Okay, so hence we have proved the following thing: if we have two chain complexes and a chain map between them, then there exists an induced homomorphism. Okay, so how we have defined this thing? So we defined that when we have Cn prime goes to Cn minus 1 coming from Cn plus 1 prime, and we have map fn, and this is Cn goes to Cn minus 1. Okay, so fn plus 1, cn minus 1, sorry, plus 1, and fn minus 1 up to so on. Okay, so what is hn of c star prime? So this is basically equal to zn c star prime with the partial, the boundary maps, and bn c star prime with partial, which are the boundary maps. Okay, now when I apply fn on these zn of c star prime, then this is contained inside of zn of c star. Similarly, if I take boundaries, then the boundaries bn of c star prime are contained inside the boundary of bn c star. Okay, so what is hn c star prime? Let's write it down again. So zn c star prime quotient with bn c star prime. And again, what is hn of c star? So this is equal to zn c star quotient with bn c star. Now when I apply fn on this, then this is contained inside this, and this is contained inside this. Okay, so in other words, when I take images of elements of z and c star prime, then they are contained in this, and this is contained inside this. So there is a well-defined homomorphism, because these cycles are contained in the cycles and boundaries are contained in the boundaries. So we can define this induced homomorphism from hn c star prime to hn c star. So given two chain complexes and a chain map between them, we can define an induced homomorphism from hn c star prime to hn c star. Exact sequence of chain complexes. So just like exact sequence of modules, we can define exact sequences of chain complexes. So we know what is a chain map. So the only condition they need to satisfy is that the image of the previous map should be equal to kernel of the front map. So in other words, we are saying that if we have three chain complexes, then and together with these P star, which is a chain map between A star and B star, and Q star, which is a chain map from B star to C star. So these chain complexes with these chain maps, so this is an exact sequence of chain complexes if and only if this happens, that for each and every n, this sequence is exact sequence. Okay, so in chain complex A star, I have elements. Okay, so an minus 1, an up to an plus 1 up to so on. Okay, so I have other elements. Similarly, I have bn minus 1, bn plus 1 up to so on. Okay, similarly I have cn minus 1, cn plus 1 up to so on. So and this P star is basically, this P star gives me a map for each and every n. So we know that if we have a chain map, then this means that it will give me homomorphism for each and every n. In other words, I have this P n minus 1, I have this Pn, I have this Pn plus 1 up to so on. Similarly, I have a chain map from B star to C star. So in other words, for each and every n, I have a homomorphism. So for Bn minus 1 to Cn minus 1, I have Qn minus 1. From Bn to Cn, I have Qn. From Bn plus 1 to Cn plus 1, I have Qn plus 1 up to so on. Okay, so now we are imposing the following condition, that this sequence of chain complexes is exact, if we have this condition for each and every n. In other words, we are imposing that this is an exact sequence. Okay, so an is a module, bn is a module, cn is a module, and we know how to define exact sequence of modules. Okay, so this part is a short exact sequence of modules if the image of Pn is equal to the kernel of Qn. Okay, so similarly we have the condition on each and every n. So in other words, this sequence is also a short exact sequence of modules, because once again an plus 1 is a module, bn plus 1 is a module, cn plus 1 is a module, pn plus 1 is a homomorphism between these two modules, qn plus 1 is R module homomorphism, and similarly, so these are all coming from for example our discussion from modules. So we know what is short exact sequence of modules, so we can say that when this sequence of modules is short exact sequence, because when so we know when the image of Pn plus 1 is equal to Qn plus 1. So we can define the exactness for each and every such part of this long chain. Okay, so we say that we have this sequence of chain complexes, then this is short exact sequence if and only if this happens, that for each and every n this little portion is short exact sequence of modules, and this little portion is exact sequence, this little portion is exact sequence of modules. So if this happens, then we say that this is a short exact sequence of chain complexes. Now we can observe that the following sequence is short exact sequence of chain complexes if and only if the following diagram is commutative, and in this diagram so basically the rows of this diagram are exact sequences and the columns are chain complexes. Okay, so why this diagram is commutative? Because we already imposed on chain maps the condition that this part should be commutative. So if I have P star from this chain complex A star to B star, then this part should be commutative, and similarly if I have a chain map from B star to C star, then this part should be commutative, and so this diagram is commutative. Now we have already seen that if we have a chain map between the two chain complexes, then how that chain map induces homomorphism between the homologies of those two chain complexes. So for example, if I have a map P from A star to B star, then there is an induced map P star from Hn A star to Hn B star. Okay, so similarly if I have a chain map Q from B star to C star, then I have Q star map from Hn B star to Hn C star. Now if we have a short exact sequence of chain complexes, then we have an extra map from Hn C star to Hn minus 1 A star. Okay, so going from Hn C star to Hn minus 1. So notice that this is Hn and this is Hn minus 1. Hn minus 1 of A star. So how this map is defined? So if I have Z belonging to this group, homological group, such that Z belongs to Z and C, so we know that Hn C star is equal to Zn C star quotient with Bn C star. So we can say that this Z is an element of Z and C star, and so it takes, so we have Z over here. Okay, so we have Z over here, and so this delta n takes Z to an element, so to this homology class square bracket W of Hn minus 1 of A star. So basically it lives, so W lives inside here. Okay, so where W is an element of Zn minus 1, and so okay, Zn minus 1 is contained in An minus 1, such that Pn minus 1 of W is equal to Bn of B, where B is an element of Bn, satisfying the condition that when I apply Qn on B, then I should get Z. Okay, so in other words, given any element of H and C star, then there exists an element Z belongs to Z and C star, which lives inside Cn. So given this Z, the image of delta n is this W, such that Pn minus 1 of W is equal to beta n of B, where B is an element of this Bn, such that Qn of B is equal to Z. Okay, so that's how we find the image under delta n of this element Z. So the image is W satisfying these conditions. Okay, now we have to show that this homomorphism, so these images, so the image of Z is equal to W, this will define a well-defined homomorphism. Okay, so let's see how to prove this result. So starting from an element of Z and C star, so of course why we have taken this, because we have considered an element of H and C star, and this Z belongs to Z and C star. So let me say again why we are taking this Z to be belonging to Z and C star, because H and C star is equal to Z and C star quotient B and C star. Okay, and the elements of this are of the form Z plus B and C star, where Z belongs to Z and C star. So we can say that we can take element, so if we are taking an element square bracket Z, a class from this homology group, then this Z is in fact an element of Z and C star. Okay, so then there exists an element B belongs to Bn, such that Qn of B is equal to Z. Okay, so why this holds? So let's go back to our picture. So if I have Z over here, okay, now this sequence is exact. So this sequence is exact because it is short exact sequence of chain complexes. Okay, so if it is short exact sequence, then this portion of modules, okay, so consisting of An, Bn and Cn, which are modules, and Pn and Qn, which are our module homomorphisms. So this little portion is exact sequence. So in other words, the image of Pn is equal to the kernel of Qn. Okay, so in other words, we can say that this Qn is surjective. Okay, so it is an onto homomorphism. So in other words, every element of Cn is image of some element of Bn, and we started from this element Z, and now we are using the surjectivity of this Qn to say that there must exist an element B belongs to Bn, such that Qn of B is equal to Z. Okay. Okay, so now using commutativity of the diagram shown in this picture, okay, so we get the following. So we have B belonging to this Bn, we have Z belonging to this Cn. So starting from Bn and following two different routes. Okay, so first apply Bn and then apply Qn minus 1, or first apply Qn and then apply gamma n. Okay, so this Qn of B is equal to Z, so this Z is basically Qn of B, so that's why this becomes gamma n of Z. Now we also know that this Z belongs to Zn of C star. So in other words, this Z is basically belongs to the kernel of partial kernel of gamma n. In other words, z or gamma n of z is equal to 0 because this belongs to the kernel of gamma n, or since this is an element of z and c star. So gamma n of z is equal to 0. So qn minus 1 of beta n of b is equal to 0. So in other words, we can say that beta n of b belongs to the kernel of qn minus 1. So basically, so this is an element. Okay, so beta n of b is an element of bn minus 1, and when I apply qn minus 1 on this, then it goes to 0. So it belongs to the kernel of this. Okay, now let's see what we have so far. So we have cn over here, we have bn over here, we have an over here. So there is z in cn, and there is b in bn, and there is qn over here, such that qn of b is equal to z. And also from this picture we have beta n of b belongs to kernel of qn minus 1. So we have beta n of b. Okay, so this has beta n of b, and it belongs to the kernel of qn minus 1. Okay, so that's what we have proved so far. Now consider the exactness of the following sequence. Okay, now we are considering this portion of the exactness of the chain complexes. Okay, now we get Pn minus 1 of an minus 1 is equal to kernel of qn minus 1 due to the exactness. So the image of Pn minus 1 must be equal to kernel of qn minus 1. Okay, so since beta n b belongs to kernel of qn minus 1, that's what we have proved in our previous discussion. So there exists w belongs to an minus 1 because the kernel of qn minus 1 is equal to the image of an minus 1 under pn minus 1. Okay, so this bn minus 1 contains, so pn minus 1 of an minus 1 is contained in bn minus 1, and in this containment, so this image is exactly equal to the kernel of qn minus 1. So that's why this bn of b must be equal to pn minus 1 of some element w. Okay, now consider the commutativity of the diagram shown in the following figure. So now we start from w. So now we have an element w in an minus 1. So when we apply alpha n minus 1 and then pn minus 2, or apply pn minus 1 first and then apply beta n minus 1, then I should get the same answer. So that portion is basically using the commutativity of the diagram. Okay, now pn minus 1 of w is equal to bnb, so this is written over here, so we are using over here. Now this is equal to 0 because this b star with these betas, the maps, is a chain complex. Okay, so its chain complex implies that beta n minus 1 composition beta n for each and every integer n. So this composition is 0. So this is the condition that we impose on chain complexes. So that's why beta n minus 1 of beta n of b is equal to 0. Now since pn minus 2 is injective, so alpha n minus 1 of w is 0. So pn minus 2 is injective because the image of this map, which is 0, must be equal to the kernel of pn minus 2. So kernel of pn minus 2 is 0. So pn minus 2 is injective using the exactness of this sequence of modules. Okay, so in other words, an injective homomorphism will take only 0 to 0. So alpha n minus 1 of w is 0. So w belongs to the kernel of this map. So basically we have w over here. So basically and alpha n minus 1 of w is 0. So w belongs to the kernel zn minus 1 of a star. Okay, so given any z in Cn, we define B, and we also shown that Pn of W, okay, so we showed over here Pn minus 1 of W is equal to beta n of B, so it's over here. So Pn minus 1, Pn minus 1 of W is equal to beta n of B. So this W is our required W, but now we just want to make sure that this is a well-defined W. So for example, if there exist two B and B prime, okay, so two elements such that Qn of B is equal to Qn of B prime, because we defined this W using this B, okay, so and we just took any B from Bn. Now we want to show that it doesn't matter if you take any B from this Bn, then this W is unique. So take two elements B and B prime such that Qn of B and Qn of B prime is equal to Z. Okay, so let W and W prime be two elements using the same arguments. So we have two elements, and both of these two elements satisfy this condition. Okay, so that's the condition. Once again, Pn minus 1 of W is equal to beta n of B, and Pn minus 1 of W prime is equal to beta n of B prime. Now Qn of B prime minus B is equal to 0, so we are just using the homomorphism property of Qn. So just take Qn of B prime on the other side, and this will be equal to 0 because both of them are equal to Z. Hence this B minus B is equal to Pn of A for some A belongs to An. So why is this the case? Because B prime minus B belongs to kernel of Qn. Okay, so Bn minus B belongs to kernel of Qn. So we know that from the exactness of this part, so this exact sequence of modules, so this little portion, so this says that the image of Pn must be equal to kernel of Qn. So in other words, this element B minus B prime is image of some element of An. Okay, so there exists A belongs to An such that this holds from the exactness of this. And now consider this, Pn minus 1 of W plus alpha n of A. So this is equal to Pn minus 1. So just using the homomorphism property, this is distributive over addition. So this is equal to this, and this goes to Pn minus 1 of W beta n Pn of A. So why is this the case? Because A is an element of An. So and we can follow two different routes. So first applying alpha n and then applying Pn minus 1, or we can follow the route first apply Pn and then apply beta n. So now using the commutativity of the diagram, we get this, and this is equal to this because Pn of A is equal to B minus B prime. Okay, so this is true, and Pn minus 1 of W, so Pn minus 1 of W is equal to beta n of B. So that's once again this condition that Pn minus 1 of W is equal to beta n of B. And using the homomorphism properties, so beta n of B and beta n of with negative sign, they will cancel out, and we will get beta n of B prime, and beta n of B prime is equal to Pn minus 1 of W prime. So basically we have shown that Pn minus 1 of W plus alpha n of A is equal to Pn minus 1 of W prime. So since Pn minus 1 is injective, so we have this Pn minus 1 and the image of W plus alpha n of A is equal to Pn minus 1 of W prime, and Pn is minus 1 is injective, so W must be equal to this. So W prime must be equal to W plus alpha n of A. And okay, so let's see, I have two elements. Okay, so basically this A belongs to An. Okay, so and this alpha n of A belongs to the boundary. So basically we can say that alpha n of A belongs to B n minus 1 of A star. Okay, and this W and W prime belongs to an minus 1, and also we have shown that this w and w prime belongs to zn minus 1 a star. Okay, so this belongs to zn minus 1 of a star. So in other words, we have two elements of the zn minus 1 a star, and they differ by an element of bn minus 1 a star. So in other words, we can say that their classes are equal because they are elements. Okay, so as an elements of zn minus 1 of a star quotient with bn minus 1 of a star. So as an element of this, if they are differing by an element of bn minus 1 a star, then they are of course the same elements. So once again, using the properties of quotient modules. So we have a map from zn c star to hn minus 1 a star. Okay, now we want to show that this map is in fact a map from hn c star to hn minus 1 a star. Okay, so first we need to show that if z and z prime are two elements such that they are equal elements, then their images under this procedure that we have already done, that there is a unique w corresponding to z in Cn, and now take two elements z and z prime such that their classes are equal, then their images are equal. That's what we want to show. And now if they are equal, then they differ by an element of the boundary, because z and z prime are elements of this, and this is equal to z and c prime quotient with b and c prime. So what is b and c prime? So b and c prime is an image of elements of Cn plus 1 under gamma n plus 1 inside Cn. So in other words, they must differ by an element of the boundary, or the boundary are the elements of which are the images of Cn plus 1 under gamma n plus 1, so they differ by this element. Moreover, now we have C inside Cn plus 1, and we have Z, which is equal to Z prime plus gamma n plus 1 of C, and this Qn plus 1 is surjective, so there exists D inside Bn plus 1 such that Qn plus 1 of D is equal to C. So that's the condition, because this is basically a short exact sequence of modules. Now choose B belongs to Bn such that Qn of B is equal to Z, and B prime is equal to B plus Bn plus 1 of D. Okay, so define this element. Now consider the following image. So the image of Qn of B prime, okay, so B prime we defined over here is equal to B plus Bn plus 1 of D, and this is equal to this, and using the homomorphism property is equal to this, and so once again Qn of B is equal to Z. Okay, and now D is an element of Bn plus 1, and first we apply basically Bn plus 1 and then we apply Qn, or we can do it the other way. So first apply Qn plus 1 and then apply gamma n plus 1. Qn plus 1 D is basically equal to C using this, and gamma n plus 1 of C is basically equal to so Z plus gamma n plus 1 of C is equal to Z prime, because that's how we define it. Now also Bn of B prime, now B prime is equal to B plus beta n plus 1 of D, so this is equal to this, and since the composition, since this portion is chain complex, so the composition of any two consecutive is 0, so that's why this becomes 0, so we have Bn of B. So basically if we have two elements Z and Z prime such that their classes are equal inside this homology group, then their images are same. So that's why we have a well-defined homomorphism from Hn of C star to Hn minus 1 of A star. Now the maps delta n that we constructed in above lemma are called connecting homomorphisms. Now we have our last important result of today's lecture. So given a short exact sequence of chain complexes. Then we have this long sequence, so Hn A star to Hn B star. So we have already seen these maps because these are induced from just the homomorphisms of so just from the chain maps of these chain complexes. Similarly, we have Q star, and these delta n's are connecting homomorphisms that we proved in our previous result. Now this theorem says that this is basically an exact sequence. Okay, so we will prove the result in 3 steps. In the first step, we will prove the exactness at the node Hn B star, and in the second step we will prove the exactness at Hn C star, and in the third step we prove the exactness at Hn A star. Okay, because these 3 are the only different possibilities, and if we can do it for these 3, then for each and every n this will be true, so it will be an exact sequence. But I'm going to show the exactness at this node, and the next 2 steps are basically very similar. So let's see how to show exactness at Hn V star. Okay, so consider the following portion of that long sequence, and we also have this condition that this composition is 0, because this is coming from the exactness of this. So the image of Pn is equal to kernel of Qn, so the composition is always 0. So in general we can write down Q star composition P star is 0 because this holds for each and every n, so we can write it like this. Okay, now the sequence can be written in the following form, and we also know that basically image of P star is contained in kernel of Q star. So this happens due to this fact, because when I apply P, so how we define this P star? So this P star is defined, so apply Pn on Zn A star, and this is contained in Zn B star. So basically we apply just B on the elements of Zn A star, and this is contained inside this. Similarly, we apply Pn on Bn A star, and this is contained in Bn B star, and that's how we define this P star. Okay, so basically we are applying Pn, and when we apply Pn first and then we apply Qn later on, then their image must be 0 using this property. So that's why we have this thing. So we can write down that the image of P star is contained in kernel of Q star, because the composition of any 2 consecutive maps over here is 0. So that's why this holds. Now we have shown that the image of P star is contained in kernel of Q star. Now we want to show the other side, that is kernel of Q star is contained in image of P star, because we want to show that at this node image of P star is equal to kernel of Q star. So let's take an element of kernel of Q star and show that it is an element of image of P star. So take an element of Zn of B, because we are taking this X to be an element of Hn of B star, and once again I can take this X to be from Zn B, such that this class belongs to kernel of Q star. Okay, so then Qn of X, okay, so this element belongs to this part. Okay, so this is X, and when I apply Qn on X, and this must be equal to gamma n plus 1 of C. Why is this the case? Because Qn of this, okay, so we are taking this Q star of this is equal to 0. Okay, so let's go back. We are saying that this element X of Hn B star, when we apply Q star on this, then I get an element of Hn C star, and it is 0 over here. Okay, now let's see what is Hn of C star. So this is equal to Zn of C star quotient with Bn of C star. So if I say that when I apply Q star on an element X, and it is equal to 0, and this 0 belongs to Hn of C star, in other words, I am saying that this element, so the image belongs to this B and C star. Okay, so once again this X, so Qn of X must belong to the boundary. Okay, so the boundary of this, so because once again Hn of C star is equal to Zn of C star quotient with Bn of C star. So when I say that an element is 0 in this, it means that it belongs to Bn of C star. So in other words, Qn of X is equal to gamma n plus 1 of C. For some C belongs to Cn plus 1. But since Qn plus 1 is surjective, so there exists D belongs to Bn plus 1 such that C is equal to Qn plus 1 D. So this C is equal to Qn plus 1 D. Now consider this element Qn of X minus beta n plus 1 D. So this is D. When we apply beta n plus 1 on this, we get an element of Bn, and I can subtract, so I can write down this element. Okay, consider this image. So this is equal to Qn of X minus Qn of Bn plus 1 of D. Okay, now Qn of X, now this is an element, so this element D of Bn plus 1. So basically we are following this route, so applying Bn plus 1 and then Qn. We can also take the other route, so first applying Qn plus 1 and then applying gamma n plus 1. So we are taking the other route, so this is replaced over here. Okay, now Qn plus 1 of D is equal to C. Okay, so we have gamma n plus 1 of C, and Qn of X remains the same, and this is equal to this because we imposed that gamma n plus 1 of C is equal to Qn of X, and this becomes 0. Okay, so hence X minus beta n plus 1 of D is equal to Pn of A for some A belongs to An, because Qn of this element is 0. So we know that using the exactness of this portion, if there exists an element of Bn such that Qn takes that element to 0, then from the condition that image of Pn is equal to the kernel of Qn, so that element is image of some element of An, and we are taking that element to be A. Okay, so also, so apply alpha n and then Pn minus 1 on A, and this must be equal to applying Pn and then beta n on this. Okay, but Pn of A is equal to X minus B beta n plus 1 of D due to this condition. Okay, so using this condition we have this. Okay, so using homomorphism property, this is equal to beta n of X is equal to beta n plus 1 of D. So this is 0 because this is a chain complex and composition of any two maps is 0. So beta n of X is 0 because X belongs to Zn of B star. So this is 0, but Pn minus 1 is injective, so alpha n of A is 0 because Pn minus 1 of alpha n A is 0, but Pn minus 1 is injective, so alpha n of A is 0. So this A, the class of this belongs to this because alpha, okay, so A belongs to the kernel. Okay, so alpha n of A is 0, so kernel of alpha n, so in other words A belongs to Zn of A star. So we can say that there exists a class of A inside this. Now a class of X is equal to class of X minus beta n plus 1 of D. So why is this the case? Because beta n plus 1 of D, so D belongs to Bn plus 1, and beta n plus 1 of D belongs to the boundary inside Bn. So I can subtract this element, and the class of this should remain the same. Okay, so but this is equal to Pn of A from our discussion above, and which is equal to P low star of A. So in other words, this X, which we take to be an element of Hn of B star, is image of some element of Hn of A. Okay, so in other words, we can say that the sequence is exact at Hn of B. Okay, so similarly, using the same arguments, we can show the step 2 and step 3, which are provided in the lecture notes. So next time we will be interested in homology groups of simplicial pairs, and we will see that how they will help us in calculating the simplicial homology and to understand homology in general. This is the end of the lecture. Thank you very much, and Allah Hafiz.